Okay, so continuing on with chapter 16. So we left off talking about phagocytosis. Just as a review, remember the neutrophils always arrive first, followed by the macrophages, because the macrophages need to transform from monocytes. And these are the really gigantic ones. Okay, so as I mentioned before, even the tiniest microscopic worm, parasitic worm, is still going to be huge in terms of comparing it to, basic, your basic bacterial cell. So there's no way that a macrophage could be able to engulf an entire worm, no matter how tiny it is. So that's what eosinophils do. So they actually excrete toxic enzymes that perforate, or which means to punch holes in the worm's body. And actually one of the chemicals they produce is called perforin, which means to perforate. Then once the worm has broken up into a bunch of pieces, then the macrophages can come in and they can phagocytize and get rid of whatever is left. Another type of cell that I want to mention that fits into non-specific or innate immunity are natural killer cells. Okay, so natural killer cells are kind of the generalized version of T cells, and specifically cytotoxic T cells, which we're going to get to in our final chapter, chapter 17. But what natural killer cells do is they're non-specific cells, and they're constantly cruising around your bloodstream, and they look for cells that look funky, okay? And what I mean by funky is cells that are starting to display abnormal proteins on their surface. And so they don't have the typical cell surface proteins that define you as being you. It's kind of weirdo proteins. And these natural killer cells will be on the lookout for those. And if they see one, they're going to destroy it. So they can also secrete chemicals that can punch holes in the cell's body. They also can release compounds that basically tell the cell, you know what, you're bad for the organism as a whole. You need to basically commit suicide. So they do that too. So cells that tend to display weird proteins are cells that have been infected with a virus. So thank God this happens, or else viruses would always be undetected in our cells, which, as we've learned, makes them especially hard to treat and especially deadly. So eventually, yeah, you're going to get some weirdo proteins on the surface. So virus-infected cells will look like this. The other types of cells will be cells that are starting to turn cancerous and become tumor cells. They also start to secrete weird proteins on their surface. And so natural killer cells also help rid your body of the beginnings of tumor cells. And it's great when you're young and you have a fully functioning immune system. You know, as our immune system tends to wear out or not function at its full capacity with age, this is why we see a lot of cancers start to appear as humans get older. And it's simply because our natural killer cells, you know, they may miss a tumor cell that, 30 years ago when you were in your 20s, they certainly would have detected. So it's just kind of like the immune system is not at tip-top shape, which it is usually in your 20s and 30s. But that's what natural killer cells are. So they are part of non-specific or innate immunity. So basically this is an eosinophil. So a couple of things I wanted to point out here. So you have the eosinophil. Here it's secreting enzymes and perforin, which are causing damage in the worm. The other thing I want to point out are these little Y-shaped molecules, which are antibodies, which we're going to get into in chapter 17, and which are part of your specific immune system. But the beauty of antibodies is anytime you have antibodies sticking to something, it is a big red flag that the macrophage or whatever, neutrophil should come in and eat that particular thing. So antibodies are a big signal to phagocytosis. So this is an electron micrograph, and this is actually a fluke, which is a type of parasite that's pretty big. And then all of these little round things here are eosinophils. So you can see the eosinophils, it's not just one or two. They will basically swarm the organism and just start secreting these proteins. And eventually, that fluke is going to die because its cell contents are going to leak out. So the cell lyses. So I just want to mention a couple of organs about the lymphatic system. We're not going into any anatomy, nothing like that. There's not going to be any diagrams. I just want to mention it because organs in the lymphatic system can function and have an immune response. Okay, so the lymphatic system, those of you who've taken A and P, I'm sure you've dissected it. It's a system of lymph nodes, lymph fluid, and then vessels, and then the lymph fluid can go back into the bloodstream. And the lymphatic system really has three functions: collects excess fluid, transports fats, but there are also many components of the immune system. So this is what I'm going to talk about. You don't need to know these two for a quiz or an exam. Okay, so you have excess tissue fluid that can drain into lymph vessels, becoming lymphatic fluid. One of the organs that's really important are lymph nodes, okay? And lymph nodes are clusters of lymphatic tissue and ducts. They're located, at the base of the neck. There's a chain of them down your sternum. You have them in the groin, behind the knees. You kind of have them all over the place. And what's great about lymph nodes is that's where a lot of your fixed macrophages are, and also some collections of antibodies. So they're really there to kind of filter your fluid and to be able to pull out any potential pathogens that are passing through your bloodstream. So this is where I want to caution you that a lot of the things, a lot of the signs and symptoms having to do with having an infection, culturally, we tend to look at them as bad. I want you to look at them in a different way and kind of think, oh, good, my immune system's working. One example of those are swollen lymph nodes. So, obviously, if you're feeling sick and you have swollen lymph nodes, go to the doctor. But the fact that they're sore means that, hey, they're working. They are filtering out something that could potentially cause an infection. Now, obviously, if you have a lump in a lymph node that's, has been there for 6 weeks, that's something definitely to get checked out. But I know when my lymph nodes get a little bit sore, I'm like, oh, good, go immune system. You're doing what you're supposed to do. Okay, so the lymph nodes, they're filled with lymphocytes, they're filled with macrophages. Their whole purpose is to filter out anything foreign and get it out of your system. Okay, next lymphatic organ I want to talk about is the thymus. And so the thymus is located behind your sternum. And in infants and children, it's actually quite big, about the size of an apple. And then through adulthood, it shrinks to be about the size of a walnut. Okay, so in all of you guys, that's the size that it is. And the reason it's important is this is where your immature cells mature into T cells, which are part of your specific immune system. So it's pretty easy to remember. T, thymus starts with T, and that's where your T cells mature. Your spleen also has an immune function because it's basically a graveyard where, phagocytic cells, your white blood cells that have served their purpose, they've phagocytized foreign material, and they kind of go to the spleen to die. Red blood cells also go there. So that's why, for example, if you've ever had mono, which is caused by Epstein-Barr virus, one of the signs of mono is that your spleen tends to be really inflamed, and that's simply because your immune system is working really hard. You have a lot of macrophages that have served their purpose, and now they're going to the spleen to be broken down so that they can be excreted. So the spleen, you can live without a spleen. It's a highly vascularized organ. So, say for example, someone is in a motor vehicle accident and they suffer some blunt force trauma to the abdomen. If their spleen is ruptured, normally that person goes right into surgery and that spleen is taken out. And it's because, the person could bleed to death internally. So you can live without a spleen kind of the way you can live without a gallbladder. I mean, they definitely have functions. You'd like to still have them, but you can live without them too. Okay, same thing with your tonsils. So your tonsils are at the back of your throat. And those of you who have had infected tonsils know that, you've probably seen them because they've been really large and inflamed. They hurt. But if possible, the tonsils should be left in. It's interesting when you look at the history of tonsillectomies. So, I was a child of the 1970s and my brothers were about a decade ahead of me. And when they were little kids, every single little kid had their tonsils out. It was kind of a rite of passage. You had to go and stay overnight in the hospital, and then you got ice cream, and but every kid had it done because it was thought that the tonsils really didn't do anything. So, before they start getting infected, let's get them out of there. And then by the time I was born, pediatricians had figured out, hey, wait a minute, your tonsils actually do have an immune function. They contain both mature T and B cells, which can help fight infections. And remember, the respiratory route is the most common entry for pathogens. So yeah, it's kind of nice to have that first line of defense right at the back of your throat. So now tonsils are only removed when they are chronically infected, or sometimes their anatomy is, they're just really irregularly shaped and convoluted, and no matter how many rounds of antibiotics, sometimes you can't get rid of an infected tonsil, and if that's the case, then they usually take them out. I had mine out at age 40, and let me tell you, that was not a picnic. It's not fun. However, I haven't had a sore throat since then, so the short-term pain was totally worth it. But they do have an immune function, so if you can keep your tonsils, definitely keep them. Okay, so now I want to talk about inflammation. Okay, and what I'm going to talk about specifically in this chapter is inflammation relating to a microorganism, which is a pathogen being introduced into your body. Okay, realize that inflammation can also happen throughout your body and not in response to a microbe. So, if you've ever fallen and twisted your ankle, yeah, you're going to have inflammation too because tissue has been damaged. So anytime there's tissue damage, your body responds with inflammation. And that can be system-wide as well, especially when we think about inflammatory bowel diseases like Crohn's disease. That is inflammation as well. Rheumatoid arthritis, is an autoimmune disease that results in severe inflammation. But what I'm going to talk about specifically is we have a microbe that's entered our body, and then this is what happens. Okay, so I know you've experienced, because all of us are old enough to probably have had an infected cut or an abscess or something at some point in our life. And so when I look at inflammation, I look at 4 main signs. Okay, for me, this final one, yeah, that's a sign. But if you've gotten to the point where your limb or whatever is inflamed is not functioning, you've got bigger problems than just simple inflammation. So for me, the 4 signs of inflammation are these 4: heat, redness, swelling, and pain. Okay, so think back to when you had an abscess or a cut. Yeah, it's probably sensitive to the touch. You have some edema in there, so it's a little swollen. It's probably red. It feels a little warmer than the surrounding tissue. That is inflammation. And there are reasons for all of those things to happen, which we're going to get into now. So inflammation has 3 functions. And remember, we're talking about a microbe here, okay? So when we talk about microbes entering the body, first, we want to kill those invading microbes. Okay, or if it's a virus, we want to inactivate that virus. Then, and that's probably 99% of inflammation. Then finally, when all of the drama is over, we want to clear away any tissue debris, and then we want to repair the injured tissue. So there are also 3 stages of inflammation. So number 1 is we need to make the blood vessels leading into the site of infection bigger so that the phagocytic cells that are pretty huge can get there. Okay, so vasodilation means increasing the diameter of blood vessels and also increasing the permeability, meaning that cells traveling to the site of infection can actually get out of those blood vessels to where the microbes are. The second stage is getting those phagocytic cells there. Okay, so neutrophils first and then the macrophages, and having them do what they have to do, which is basically eating everything that is foreign and that shouldn't be there. And then finally, the third stage is repairing that tissue. And of course, that varies depending on what type of tissue we're talking about. So, skin tissue, that's going to repair pretty quickly. If it's bone, that's going to take much longer. It depends on the type of tissue where the inflammation occurred. So first, let's talk about vasodilation. And I'm going to go back to a term that we discussed in the previous video, which is chemotaxis. Okay, so remember, the neutrophils and the macrophages are stimulated by certain chemicals traveling through the blood. And traveling through the blood is the process of chemotaxis, and the chemicals that we're talking about are cytokines. So the primary cytokine that's going to be released when your cells are damaged is histamine. Okay, and remember, it can be other things too, like parts of a viral capsid, parts of damaged bacteria, some of your cellular components that are on the outside instead of the inside. But the primary cytokine that's going to start the process of vasodilation is histamine. And so when histamine is released, it's going to diffuse into capillaries near where the infection is and cause them to dilate or become larger, and it's also going to make them more permeable. So remember, when capillaries are tiny blood vessels and they are only 1 cell thick, and so when those cells expand, there's going to be spaces in between them, and that's actually needed to get those gigantic phagocytic cells out into the site of infection. Okay, so the diameter of the vessels are going to increase, and this is where we see the redness and the warmth, because when you increase diameter, that means we're going to get more blood flow to the area. The skin is going to become red and warm simply because more blood flow. And you're going to have more fluid move into the tissue. That's where the swelling comes from. But the good thing is that fluid and increased blood flow is now going to bring in neutrophils, and then it's going to bring in macrophages. If the infection is strong enough, especially if you've had an abscess, you may see pus form. Now, pus is gross. Okay, I think we all know what it looks like. However, if you think of it in a clinical term, so all pus is white blood cells, your neutrophils and your macrophages that have given their lives and phagocytized material. It's damaged or dead microbes, and then it's just tissue debris. I don't know, maybe that makes it a little less gross. Okay, it's just kind of the byproduct of fighting an infection. So once we have vasodilation occur, then those phagocytic cells are going to get there. Okay, so the other thing that histamine is going to do besides trigger vasodilation, it's also going to signal, hey, neutrophils, you need to get here first. And then monocytes, start turning yourselves into macrophages because we're going to need you too. Now, I mentioned how big those cells were. And so they need to be able to squeeze out between the cells of capillaries. And we actually have a name for that process. It's called diapedesis. Okay, so that's where these gigantic cells are able to squeeze out in between gaps of capillaries due to vasodilation. And then the phagocytes are going to get there. They're going to do what they're supposed to do, which is to detect and inject or ingest the, the bad guys that are there. And then the final stage of inflammation, once everything is cleared away, then you're going to have new capillaries grow into the damaged area, and depending on the tissue type, eventually that tissue is going to be repaired. Not that you might not have scar tissue there, but it is going to be repaired. So here is the process that we're talking about. Let's say that there's a knife with some bacteria. Maybe you're working in the kitchen and you accidentally cut yourself. If it gets down to the level of the dermis where there's a blood supply, yep, okay, so those microbes have been introduced into the dermis. Microbes are going to do what microbes are going to do. If it's bacteria, the bacteria is going to be in that nutrient-rich environment, and they're going to start growing and reproducing. But once they do that, then they're going to trigger histamine, other things to be released to be able to signal the process of inflammation to start. So there's histamine, there's prostaglandins, kinins, leukotrienes. All of these are cytokines, but the primary cytokine is histamine. Okay, and so what this is right here, this is warfare. So you have vasodilation occurring, you have hopefully, the phagocytes getting there pretty quickly, and then, pus may be a byproduct of that. Okay, this shows the process of diapedesis. So neutrophils are pretty big. Look here, here's the tiny little bacteria. So the neutrophils are big, the macrophages are gigantic. And so diapedesis is when, due to vasodilation, there's these little gaps produced in the capillaries. And so now they're able to squeeze out in between those gaps in the capillaries. And then finally, after they've done what they've done, then we have a scab, we have a blood clot, new capillaries grow into the area, and then the tissue repairs itself. Okay, so I'm at 22 minutes. This is where I'm going to stop. We'll have one final video having to do with chapter 16, and then we'll move on to 17. Thank you.